Yes, thank you for the introduction. So my name is Johan Pilhagen, and I work at research and development at Outokumpu Stainless, which is a steel producer and located in Avesta and in Sweden. And I will present today the results from a Swedish research project called HIMEC2. It's financed by the Vinnova, Swedish Innovation Agency, and the Strategic Innovation Program Metallic Materials, and the coordinator is the Swedish Metal Research Institute. And the time frame is a 3-year project, and next year it's 1 year to go. And we have a quite nice collaboration of industrial partners from, let's see what is, sorry. That was difficult. From iron ore production, LKAB, we have 3 steel producers, Outokumpu, Ovako, and SSAB, and also a welding company, ESAB, and also different companies utilizing these metallic materials. So we have 3 different areas of interest: hydrogen for power generation and heating technologies, automotive, and what I will talk about today, which is the storage and transportation of hydrogen. So in this project, we have chosen to use this hollow specimen method. And it's basically a cylindrical specimen. We drill a hole and you fill it with hydrogen gas. And we have utilized slow strain rate testing, but you can also use fatigue testing. So the testing parameters was 200 bar hydrogen gas or argon gas as reference. And the testing temperatures was -50, 20, and 100 degrees Celsius. And the main benefit of this testing method compared to autoclave is that you have a lower cost. You don't need to invest in an autoclave, and lower hydrogen consumption. And you can also easily instrument your specimen. Not only for this kind of strain gauges or extensometer, but you can also apply fluoroscope, acoustics, or if you want to put it in an X-ray or neutron source. And typically when you measuring the hydrogen embrittlement, you use the area reduction or the fracture elongation. But we saw that in these kind of hollow specimens, you typically get a pressure drop. And that's because the fracture happens not entirely on the entire specimen, but you get the surface cracks before. And then you lose the pressure. So we decided to define it as the elongation to the pressure drop. And here's an example of the fracture surfaces. So this is one 316L, 4404, tested at -50. So you have the argon gas on the left and the hydrogen gas on the right here. And we can clearly see this kind of embrittlement in the hydrogen gas environment. So stainless steels are commonly used for these applications, but there are still some knowledge gaps, particularly if you want to introduce a new grade or utilize higher strengths that was conventionally used. And there's also a lot of activities in, you can say, large-scale hydrogen storage, which brings up new questions. So in this project, we looked at 3 different austenitic stainless steels. 2 of them are this 316L in American grade specification. In the European grade, it's actually 2 different grades, 4404 and 4435. And the main difference here is slightly different content of chromium, molybdenum, and nickel. And in this project, we were interested in the nickel content. So in principle, we have one 316L with low nickel content and one 316L with high nickel content. And then we also have another grade, 4420, which is you can call a lean 316 grade. And the idea here is to make it more cost-effective by reducing the molybdenum and nickel, which is the most costly elements. So here we have an increased chromium content to compensate for the molybdenum. and an increased nitrogen to compensate for the lower nickel. And by using nitrogen as an alloy addition, you also get a higher strength in the material, as you can see in this posting. And in the table to the right, you have this nickel equivalent. And you can see the equation here. There's several versions, but we're using this Sunglass equation. It's also add a contribution from the nitrogen. And the reason why we're interested in nickel, or it's called nickel equivalent, is that it seems like from the literature that the hydrogen embrittlement, at least in the SSRT condition, is due to this susceptibility for strain-induced martensite. And if you look in the different standards and norms, they typically specify a nickel content of 12.5 or 13 weight percent for hydrogen gas applications. So the austenite stability is a important thing to consider. So this nickel equivalent is a way to also include the other elements on this stability. And here we have an example of the stability of the austenite. So we have these EBSD maps. They formed up to around uniform elongation in argon atmosphere at room temperature. So to the left, we have this 304, which is a lower alloy grade, austenitic stainless steels. And you can see it mostly transformed into martensites, which is the red color. But if you look at the 316, you can see that if you ignore this kind of martensite region at the crack, it mostly consists of this blue and yellow color. And the yellow indicates regions where you have mechanical twinning, and the green is where you have started to have martensite transformation. So at uniform elongation for the 304, it's fully transformed to martensite, which is the TRIP stands for transformation-induced plasticity. And for the 316, it seems like first you have mechanical twinning, and then you have martensite nucleated on these twinned regions. I know I didn't talk about stacking fault energies, but that's an important concept. And it gives some explanation, but not for fully explained for when you use nitrogen addition in the alloy. So here we see some engineering stress strain curves for the 3 different grades. So we can see for the 4435 with the highest nickel equivalent, it doesn't seem to be degraded by the hydrogen. You have some martensite formation in the necking region at -50. And for the 4420, you have no embrittlement at room temperature, but it fails around the necking region at -50. And perhaps for the 4404, which is the most interesting for the research community, here's a lot of things happens. So we can see that at elevated temperatures, you have no observed embrittlement, but it embrittles at room temperature, and even more embrittled at -50. And you can also see some interesting things like you have a lot of deviation in the load at room temperature, but you don't see it in, for example, at -50. So that perhaps indicates different cracking behavior, like crack propagation and arrest. And you can also see that at around 20% engineering strain, the strength starts to increase rapidly. And that's because of the trip or whip effect in the material. And that's even more evident if you do look at this work hardening rate, as you can see in this figure. So the bump here comes from the activation of martensite formation and mechanical twinning. And we can also see that in the hydrogen atmosphere, it actually breaks when this kind of strengthening mechanism starts to kick in. So that's also a good indication that it's related to this stability of the austenite. And we also measured the hydrogen uptake, and we used this thermal desorption mass spectra. So we heat up the sample and measuring the hydrogen desorption rate. So the black curve here is the reference. It's the non-deformed. And the orange and green are the ones that has been after testing in slow strain rate and also at 100 degrees Celsius. So what we can see is that from the production, those austenitic stainless steels have a quite high hydrogen content, but it's mainly located in the high temperature parts, which is the strong traps or deeply traps. And we see that upon deformation, it seems like you redistribute some of the hydrogen to the lower traps. You can see the peak here at around 250 degrees Celsius. And the reason why we believe it's actually from the deformation and not pick up during the testing is that you can integrate these curves and see the total hydrogen content, and it is in principle the same. And we also verified it by melt extraction, and also I think we did a test in argon gas and saw the same thing. So one other conclusion is that there is no observed macroscopic hydrogen uptake, but we do have an embrittlement in some cases, so that indicates that the uptake is only on a microscopic level. And here we have the results. If you look at this relative elongation, and this is the pressure drop. So we see that we have an influence on both the testing temperature and the alloying in the steel. And here's a reference to Mr. Ogata, which also tested the similar grades at different temperatures. So we can see that the trend line are similar. And if you look at the room temperature, we have 4 data points. We can make a trend line. And in this case, you can see that we found a threshold of nickel equivalent 27.7 weight%. And there are other studies that some similar things. So this is in kind of that range. And this also indicates that the nickel equivalent is a better indicator than the nickel alone for these grades. And I think the main takeaway here is that it's not enough to just state the grade. You also need to give information about the composition, or as in nickel equivalent. So for example, this 44, you can actually buy a steel which has low nickel equivalent or high nickel equivalent. And it's the same grade, but they will have different behavior in hydrogen. So to summarize, 3 austenitic stainless steels with different nickel equivalents has been tested with this hollow specimen method into 200 bar hydrogen gas at 3 different testing temperatures. The susceptibility of hydrogen embrittlement increased with lower testing temperature and lower nickel equivalent values. The hydrogen embrittlement correlates well with the nickel equivalent for these grades, and we found a threshold value of 27.7. We observed no microscopic hydrogen uptake, which indicates that the hydrogen uptake relevant for the embrittlement occurred on a microscopic level. And we also observed deformation-assisted hydrogen redistribution from strongly trapped hydrogen to weaker hydrogen trapping sites when deformed. Thank you.